Hello, everybody. Um, the we finished talking about binary trees, and we talked about binary heaps. Now I want to continue on the same general area and talk about a special kind of binary tree. This tree was invented uh, in the 1960s, I think, by two Soviet mathematicians, Gregory Alekson-Velsky and Evgeny Landis. And I have no idea how to pronounce those, but I won't try. And because of their initials, we call this the AVL tree. An AVL tree is first and foremost a binary search tree. So it still has the rule that from any node, if you have something, if you have a key that is larger than the key in that node, it goes to the right. And if you have a key that's less than the key in that node, it goes to the left. So that doesn't change. The problem is we want a tree that isn't long and straggly. We want a bushy tree. We want it to be full. So we're going, the AVL tree is always going to be a balanced tree. Now, to define balanced, first you have to define height. The height is just the number of levels in the tree. So if you had just the root, that would be a height of 1. If you had the root and one child, that would be a height of 2. If you had the root, children, and grandchildren, that would be a height of 3, and so on. The balance factor of the node is the height of the left subtree minus the height of the right subtree. Now, the rule is that if we want an AVL tree, we can never let that balance get out of the range -1, 0, 1. We can't let it be -2. We can't let it be 2. So every time we insert a node, we have to make sure that we rebalance the tree to make it an AVL tree. Now, this isn't trivial. There's a lot of moves of pointers and everything. But before you panic, I'm going to be giving you a program that does it all, does all the rotations. I didn't write it. I got it from a website, and I'm quoting the website, so I'm not stealing from it. Now, just to make sure you understand, this tree here is a simple tree, and it has a height of 3. At 10, the node with 10 in it, the left subtree is 0. The right subtree has 2, nodes 20 and 30. So the balance factor at the node 10 is -2. Now, every time this tree, say we just put 30 into this tree. So we inserted 10, 20, and 30 in that order. Well, that's not a balanced tree. So how do we fix it? Well, there's a very complicated system. It says to insert that, we went left, left. To fix it, we have to go right, right. So we have to take the 10 and move it to the right, and we have to take the 20 and move it to the right. What that means is that we end up with this. The 10 is moved to the right, and the 20 has moved to the right, if you look at this tree. Now, that's the easy example. Now, suppose we add 40 and 45. Well, we essentially have the same problem. At 30, we're out of balance. So we move the 40 up pardon me, we move the 40 to the right and the 30 to the right, and we get a balanced tree. So the balance was at the -2 there at the 30, and we moved those around. Moved it to the right, and then we moved the 40 to the right. Now, a more complicated one is this here. This one is difficult. I've added nodes, quite a few of them, and now as I add the node 53, I'm out of balance for, I think, the first time. The out of balance is actually at node 45 and node 40. But I'm going to begin with node 45. And the problem here is I do this in 2 steps. First, I look below the 45 and I take the 60, 50, and 53 and I rearrange it. So I get 60, 53, and 50. Basically what I did was I moved the 53 right and the 50 right. So now it's still out of balance. But now I do the same problem, the same kind of thing up at the 45. So now at the 45, I move the 45 right, I move the 60 right, and everything else follows in order, I believe. The 60 gets the 45. The 63 is promoted. That's not 63. It's it shouldn't be there. That should be the 53. Pardon me. The 53 got promoted because it was up here, 60 over, 53 over, and the 50 is still attached to the 53, and the 65 is now made a child of the 53. It was a child of the 60. It's now a child of the 60 of the 53. What I moved in there, and as you can see, it is now balanced. Now to do all this, I went to a website, and I don't see any reason why I should reproduce the. I should reproduce everything. I will give you this particular algorithm. It's a long algorithm, but it has everything in it. What it has is it has an AVL tree, which is I made a class or some. The struct AVL has a value and a left child and a right child, and R is such a tree. R points to such a tree. You can do that. You can declare it that way. You didn't have to. You could declare it other ways too. Pardon me. R points to that structure. Now we define the class of the AVL tree, and we just make everything public. It has every node in it has a height. The tree has a height. There's a difference. There's methods to do a right rotation, right, left, left, R left, balance, and insert. So all of those are there. You can see that the rotates and the balances return trees. Now, I've been noticing that you don't seem to understand that in some of the homeworks. I've been talking to you about one-on-one. If a function returns something, you can't just have it plop the function in the middle of a line and not take its value into some variable. And the usual way the recursions work is that you return a value to something, and that gets returned, and then that gets returned, and that gets returned, and it goes back to the top. Now, the tree starts out no. And these are all simple definitions. You can write those. These get a little more complicated. They're two-step rotations in many respects. Then you have a very nice function called show. And they give you all three orders: in order, pre-order, and post-order of the trees. And it gives you a menu to choose what you want to do. Now I'm going to run this program and we'll see how it works. Now I didn't put it up there, but I think I can find it pretty fast. Here we are. And it's the AVL tree. So what I'm going to do is I'm going to run the program. And the first thing I will do is I will insert 300. Then I will insert 210. And then I will insert 200. Now at that point, the tree's unbalanced. It's 300, goes down to 210, goes down to 200. I want to see what the tree looks like. So I do a 2 to show it. Now this is kind of, I don't know where they came up with this notation. The way I read it is 210 is the root of the tree, and the two sides of that are the children of the root. So 210 goes to 300, and on one side, but they reverse it. What's left is right, and what's right is left. The 200 is the left subtree of the root, and the 300 is the right subtree of the root. The easier way to see that that's working is to do a pre-order transversal. The pre-order transversal, if you remember, writes the value in the node, and then the left subtree and the right subtree. So the value in the root is 210, and the left subtree is 200, and the right subtree is 300. So it worked. Now let's add a few more items. Let's add 4, 12. Let's add 5, 23. Let's add 199. And now let's look at the pre-order of the tree again. So I'll do a 4. I didn't do a 4, pardon me. Oh, I did. It's right there. It's hard to see. The pre-order, the root is 210. Then 200 is the root of the left subtree, and 199 is the child of 200. That's the left subtree. The right subtree has a root of 412, and it has a left subtree of 300. And a right subtree of 523. So it is a balanced tree. This is pretty nice. It's a nice little program, and I plan to use it for a homework where you're going to have to modify it a little. But I think it works pretty well right now. So that's what I want to talk. That's the end of what I want to say right at the moment. There's going to be more trees. We still have the red black, pardon me, the red black tree, and then we have B-star trees. Now, many of these trees are used in applications that you're interested in. For example, the AVL tree is used in some databases. If you look at, I'll get out of this, and I'll go back to the notes that I will be sending you. I looked on the web to make sure I could understand exactly when we use these. The suggestion is that an AVL tree is better if you do a lot of insertions and deletions as well as searches. Otherwise, the tree becomes becomes straggly, and it defeats the purpose. So I think the most important thing to remember is an AVL tree is a binary search tree. It just has an additional property that it always stays balanced. So that's it for now. I'll be posting this in a few minutes, and have a nice weekend if possible. So long now.